Hello everybody, welcome to our next lesson, which is all about probability rules. The essential question for today is, what is a probability model and what are the complement and addition rules? Now, the best way to look at probability is intuitively. You guys have a very clear understanding of what probability means, and I never want to take that away from you. So despite the fact that we are going to learn some specific rules today, I want you to always remember to think about this intuitively. And we're going to jump into that with an example, a pretty classic one, dealing with a standard deck of cards. So let's go ahead and consider a standard deck of playing cards. In total, there are 52 cards. 13 cards of each of 4 suits. Those are clubs, spades, hearts, and diamonds. The red cards are your hearts and diamonds, and the black cards are your spades and clubs. In each suit are cards 2 through 10, a jack, a queen, a king, and an ace. Now, jack, queens, and kings each carry a value of 10, while the ace can take a value of 1 or 11. We are going to consider drawing a card at random. Let Q represent that the card is a queen, FC will represent that a card is a face card, and S represents that the card is a spade. R is going to represent that the card is red, and we're going to find several probabilities in this scenario. Now, before we go any further, let's make some additional notes off to the side about playing cards. So the first thing to note is that there are 13 cards of each of 4 suits, which means there's 4 of each kind of card, the 2 through 10, the jack, the queen, the king, and the ace. So there are 4 aces, 4 kings, 4 queens, 4 jacks, etc. Second, face cards. The face cards are the cards that actually have faces on them. So those are your jacks, your queens, and your kings. Again, there are 4 of each of those face cards. Now, we don't really need to know the numerical values for the rest of these, but they might come into play later. So let's go ahead and try to articulate some of these probabilities that we want. The first thing that we want to try and find is this value here, P of Q. That's how we can read it. But the long form of that notation reads as the probability that a randomly selected card is a queen. So the capital P is always going to stand for probability, and then the capital letter next to it is going to represent whatever the event is that we are considering. It's the event we want to see. And we want to see that a card is a queen. So in order to determine the probability, we look at, well, how many cards are we actually pulling from? If it's a full deck, there are 52 cards. So out of those 52, how many indeed are queens? Well, if we said there's 4 of each card, that means there's 4 queens. That's 4 out of 52. And it's that simple. That's all you need to do. You don't even have to reduce the fraction. You can leave it like this. If you want to, you can go ahead and write it as a percentage or as a proportion, meaning a decimal between 0 and 1. But for our purposes now, I'm going to leave it as a fraction. Now, the next outcome is that the probability is a face card, FC. Well, as we said, the face cards are jacks, queens, and kings, and there are 4 of each of those. So if there are 4 of each, and there are 3 types of face cards, that means there's 4 times 3, or 12, out of the 52 cards in total. So if we're drawing randomly, we have a 12 out of 52 chance. Now, alternatively, we want to find out next the probability that something is not a face card, not FC. Well, if there are 12 total cards that are face cards, and there are 52 cards in total, that must mean the difference between those 52 total cards, take away the 12 that are the face cards, that's going to show me how many cards in total are not face cards. And again, this is out of our 52, so the probability that a randomly selected card is not a face card is 40 out of 52. So for the remaining 2, P of S and P of R, take just about 30 seconds to write out those fractions. And hit pause while you do that, and then check your work. All right, so P of S, the probability that we had a spade, that's just one of the suits. We know there are 13 in each suit, so that means there's 13 out of 52. And then for the probability of a red card, well, half of our cards are red because we had 2 suits that are red, and each of those with 13 cards in them, giving us the 26 out of 52. Now, for the next set, P of Q and S, we're still only drawing 1 card, but we want to know what's the probability that card is both a queen and a spade. And we think, okay, well, there are 4 queens, but how many of those queens are spades? And there's only 1 of them. So it's just 1 out of 52. When we see this phrase and, it has to meet both of those conditions, being a queen and being a spade, and there's only one of those in the deck. Now, the next one, the difference is we're looking at or. So it meets either one of these conditions. So queen or a spade. And we know there are 4 queens in total, but then we say how many spades are there? There's 13. But we have to pause and think, we've already accounted for one of those spades when we looked at the 4 queens in general. So there's 4 queens, one of them's a spade, and there are 12 more cards that meet that condition of being a spade. So adding those together, and we end up with 16 out of 52 that will be either a queen or they will be a spade. The next two, probability that a card is a spade or it's a red, well, there are 13 total spades and there are 26 total red cards. But since all of the spades are all black cards, there's no overlap. So we can just add those. We're not double counting anything potentially. So we just have 13 and 26 together, which is going to give us 39 out of 52 probability that a card is going to either be a spade or a red. And then finally, what's the probability the card is a spade and a red? And we actually think like, well, this card is black and these cards are all red. So that means there are no cards that are going to be both black and red at the same time. Since it's and, it has to meet both of those conditions. Since there are no cards that meet both of those conditions, we say the probability is 0 out of 52. So pretty straightforward with probability. We want to remind you of stuff that you've already intuitively understood and done before we really get into the formal definitions here. So let's go ahead and do those formal definitions now. First, probability of any event. Probability of A. A is just some event such as getting a queen or getting a heart or something like that. And it's the number of outcomes that fit that condition. So we use lowercase n to represent number in this case, divided by the number in your total, however many you are pulling from to begin with. Now, I like to think about this in a much more simplified way without any extra notation. Probability is very simple. If there's one thing that you can take away from this entire lesson, that probability can be found as this: the fraction of what you want to see divided by the total number of possible outcomes. Want over total. If you can remember that with probability, you're going to go far. Now, let's talk about some more formal definitions and see how they align with what we talked about here. First, an event. An event is just a collection of outcomes in any chance event. So, such as drawing a card when you want to know the event of getting a spade or a red or a face card, something like that. Usually with events, those are capital letters like A or B or C or some collection of those like FC representing face cards. We just have to define what those events are. The other one, the next term is a complement. And the complement, we're not saying something nice, it's something that makes something complete. And the way we think about that is that it's the probability that an outcome doesn't occur. So complement in the probability sense refers to the word not. It's the opposite of something. And we note that with superscripts, like little exponents. So here we would read that as a complement. So the probability that A does not occur is a complement. Or sometimes we'll see the little apostrophe next to the A, and we read that as A prime. Okay? And so whenever we see that, you can read it as A complement, you can read it as A prime, or you can also read that as not A. And so we go back up to our original examples, and we can see that we did indeed have a complement, and that was when we were looking right here at not FC. We knew the probability of there being a face card, so we wanted to see the complement of that with the probability of being not a face card. Now, two other things you guys will probably remember from geometry and from even elementary school looking at Venn diagrams. We look at the intersection. That's the probability that both outcomes occur. And the special word we use whenever we are talking about intersection is it's the key word and is used, meaning it has to satisfy both conditions. Okay? The other special one is union, and that's the probability that either outcome occurs. And when we're talking about union, the special word that we will usually use for union is or, and it's an either or situation. Okay? So, what notation do we use for intersection? Well, the notation we use for intersection is going to be this upside down U. Kind of looks like an N. And so I always thought of that as like, hey, if it looks like an N, that kind of looks like and. Okay? So we read this as the probability of A intersection B or the probability of A and B. Again, the special thing about intersection is to note that it must be that both A and B are met as conditions for something to be valid and included in that probability. For union, the symbol we use is the upturned U, and that kind of makes sense because of the word union. So here, if we see this symbol, that means the probability of A or B. Okay? Now, the last special thing that we want to talk about on this page is the probability of A and B equaling 0 means that something is mutually exclusive. Two events cannot simultaneously occur, essentially. Okay? If the intersection between these two is equal to 0, that means they are mutually exclusive. They cannot occur together. The other word we use to describe that is disjoint. And an example that we had up here of mutually exclusive events would be that a card is both a spade and a card is red. Those two things cannot exist simultaneously, so the intersection probability was equal to 0. And those are mutually exclusive events. Now, turn the page over so we can start to look at some other probability models and answer some more probability questions. All right, so up next we look at probability models or probability distributions. This is usually how a probability scenario is going to be laid out in front of you in a statistics problem. So a probability model is very simply the collection of all possible outcomes of chance events and their probabilities. That's what we call a probability model or a probability distribution. The sample space shows us the set of all possible outcomes. So this is our sample space, the way that we have defined it, of drawing some kind of random card. That card can be either a number card, it can be a face card, or it can be an ace. There's no other possible way that that can happen. So let's try and find the probability of each of these and examine some things about the sample space. First off, probability of getting an ace, that's pretty easy. We know that there are 4 of every type of card, so that's 4 out of 52. Now, for the face cards, we answered that question earlier on, and we know that there are only 12 face cards in total out of 52. Okay? And then finally, our number cards. Well, if cards are either face cards, aces, or number cards, then the only other outcome is number cards. So we have 16 cards in total right now that we have accounted for, and there are 52 cards in total. If we were to take those cards away from the 52 in total, we would end up with 36. So that means there must be 36 total number cards in total. Now, adding all of these up, we should see a pretty obvious fact that's true of every single sample space, and that is if we add up the probability of all of these cards, we should end up with a probability of 1. And that should make sense because we've accounted for all possible cards, all possible outcomes, and there are 52 total cards. That must mean we have 52 possible outcomes. So every time the sample space will always sum up to 1. The sum of all probabilities in any sample space will always add up to 1 every single time. So given this, we can answer these questions pretty easily. Probability of ace is right there given to us, 4 out of 52. So that's no problem. Out of 52, there are 4 aces. Probability that a card is a number card or an ace means we want to consider the possibility that a card is either a number card or an ace. And since there's no overlap between these two, all we have to do is add the two possible outcomes together. 36 plus 4 out of 52 shows me there are 40 out of 52 cards that are either number cards or aces. The next one, we've got a union of 3 outcomes, number cards, faces, or aces. Well, that means a card can be either a number card or a face card or an ace. Adding all 3 of those together gives us our grand total of 52 out of 52. And if you wanted to leave that as 1, you absolutely could. That just shows us the outcome is indeed certain. You will have one of these 3 types of cards. Finally, we have N prime and A prime, which means not a number card and not an ace. So what kind of cards are neither number cards nor are they aces? The only one that fits both of those characteristics are the face cards, and that's 12 out of 52. Now, often with probability, we don't look at only one possible event, we look at multiple possible events. Even if we're only drawing one card or having one thing happen, it might meet multiple conditions or multiple events. And so in this case, we would look at two-way tables. And so in this case, I want to consider the possibility that your card is either going to be a face card or it's going to be a heart. And whenever we're creating a two-way table like this, we can often look at it as well, is it a face card or is it a non-face card? So we break it down into those two possibilities. We could also see something be a heart or not a heart, breaking it down into those possibilities. Now, ultimately, our total number of cards will be the intersection between these two rows and columns, the total and total row and column. And that is going to show us how many cards we have in total. Now, in this example, we're going to do things a little bit differently. We're going to use the counts to represent all of these instead of the probabilities. So that's something you absolutely can do. You can have in tables represent your probabilities. You can use counts, or you can use fractions, or you can use proportions or decimal values to represent all of your chance outcomes. Any one of them is fine. Sometimes it's easier just to work with the counts. You're not always working in fractions. So in this case, I'm not looking at each one as representing a probability in and of itself, but I'm looking at how many fit each of the categories. And so the first thing I want to look at is how many hearts do we have? So how many hearts in total? That's going to show me right here the intersection between those two cells. In total, we should know that we have 13 hearts. And if we have 13 hearts, the remaining cards here must indeed be not hearts. And so those are 52 minus 13, or 39. And that should make sense because the sum of all of our hearts and non-hearts must add up to 52. We can also do the same thing by looking at face cards. We determined earlier on that there were indeed 12 total face cards. If there are 12 total face cards, that must mean there are 52 minus 12, or 40 non-face cards. We can also fill in the remaining gaps here by looking at the intersection of each event and seeing what matches each. So, what's the intersection between hearts and face cards? So this cell is going to represent the probability that a card is a heart and a face card. And this is why we refer to it as the intersection probability, because it's the intersection of the heart row and the face card column. It's that cell that intersects it. So what is the intersection between hearts and face cards? It's all cards that are both hearts and face cards. So all cards that are both hearts and face cards, of the 13 hearts we have, we know there's a jack, queen, and king. Of the 13 diamonds, we know there's a jack, queen, and king. And that's going to give us a total of, we don't care about diamonds, we only care about the hearts. Let's try that again. 3, 2, 1. Of the 13 hearts we have, there are only 3 face cards, a jack, a queen, and a king. So there are 3 that meet exactly that criteria. Now we can just use logic to figure out the rest of these. And again, using the complement idea to see what's the opposite of something happening. So here, if we have 3 total face cards that are hearts and 13 in total, that must mean the complement will be 13 minus 3, or 10 total hearts that are not face cards. We can also use that going down in the columns as well. If there are 40 total non-face cards, we've accounted for 10 of them already that are hearts. That must mean there are 30 non-hearts to give us the 10 plus 30 equaling 40. And by the same token, if there are 12 total face cards, we've accounted for 3 of them already as hearts. That must mean there are 9 total non-heart face cards. And with that, we can ultimately find the remaining probabilities that we want to see. So the probability that something is a heart, well, that looks like all the things that represent being a heart. There are 13 in total that are hearts, and that's 13 out of 52. For those that are non-face cards, we look at everything that fits into that category of non-face cards, and in total there were 40 of them. So that means there are 40 out of 52 non-face cards. For something that is both a heart and a non-face card, the intersection between heart And non-face card, the intersection between those two is 10, which means there are 10 out of 52 cards that meet that criteria. And then finally, we have those that are hearts or non-face cards. The union is a little bit trickier, and here's how I like to look at it. Does the particular cell I'm looking at meet either of those two conditions? If so, I'm going to include it. So the first one I look at is this 3. Is that card a heart? We say yes, it is, so that's going to be included. What about this 10? Are these 10 cards hearts? Yes, they are, so they will be included. What about this 9? Are these cards hearts? No, they are not, but are they non-face cards? No, they're not either. So this 9 does not get included because it does not meet the condition of being a heart, and it does not meet the condition of being a non-face card. It has to meet one of those 3 conditions, okay, or one of those 2 conditions, and it doesn't meet either. The final cell that we would look at is this 30. Do those 30 meet either one of those conditions? Well, it's not a heart, but it is a non-face card, so it does get included in our total. So we have 3 plus 10 plus 30 out of 52, giving us a total of 43 total cards that are non-face cards. And that, my friends, is the basics of probability. Let's now talk about some probability facts to kind of formalize everything that we've talked about. All right, so some of the basic probability facts that you must know. First, probability is always going to be a number between 0 and 1 every single time. If you get a probability that is more than 1, that means you have something that happened more than 100% of the time, and we should know that's just not possible. Also, we can't have negative probabilities. Something cannot happen less than 0% of the time. If the probability is 0, it is an impossible outcome. If the probability is 1, then it is a certain outcome. It will definitely happen. Next is the complement rule. We've actually used many times already. The complement rule says that the complement is found by taking 1 and subtract from it the probability of that event actually happening. So that's like in this instance where we said, hey, if we want to know what's the probability of getting a non-face card, we say if we know there are 13 cards in total, we take away the actual event of that happening. Okay? Now, up next, we have the sum of all possible outcomes in a sample space is always going to be equal to 1. We discussed that last time. And the last thing is what we call the general addition rule. Now, the general addition rule is a way to calculate the probability of a union event, so the probability of A or B. And so we can look at that as trying to find, let's say, the probability that we get the heart or non-face card that we saw here, and see how that should give us 43 out of 52. So I showed you a more intuitive way of doing this. I like to also illustrate this idea of where the general addition rule comes from. Well, a lot of students will just think, let's look at the probability of the card being a heart, and that's 13 out of 52, and then add to that the probability that is a non-face card, and that's 40 out of 52. And if we were to add together those two things, 13 plus 40, we would end up with 53 out of 52. But then that violates the first rule of probability, that we must be between 0 and 1. So clearly, this cannot work. Why? Because we have counted something twice, and that is the intersection probability. We were trying to find the probability that something was a heart or a non-face card, and what ended up happening was the probability of having a heart and it being a face card was double counted. This 10 was highlighted twice, which means it was counted twice. And if we take away that 10, we will end up with the requisite 43 out of 52 that we were looking for. So that shows us that the probability of the union of two events is equal to the probability of the first event, probability of A, plus the probability of B, but then taking away the intersection of those two events. And that is all we need to know for the basics of probability in this lesson. Thank you guys very much for watching. Have a wonderful day. Get started on your practice, work together, and come ready with questions next time.